On October 29th, 3I/Atlas will vanish behind the Sun. Just as Avi Loeb claims this massive, fast-moving interstellar object could execute a hidden maneuver that traps it in our solar system forever. The official story says it's a fleeting comet. Yet, the early data makes that hard to swallow. A nucleus possibly 20 kilometers wide, weighing more than 33 billion tons, all while showing nearly zero non-gravitational acceleration despite eruptive outgassing. If Loeb is right, we may be witnessing the first interstellar visitor to remain with us, and we'll have no way to watch what happens at the defining moment. What are we missing during that solar blackout? And who will be proven right when Atlas reemerges? October 29th draws a hard line across the calendar. On that day, 3I/Atlas slips into the blinding region behind the Sun, cutting off every Earth-based telescope. The geometry is relentless. Earth, Sun, and comet locked in a straight line with our planet on the wrong side of the glare. For nearly 6 weeks, the most massive interstellar object ever detected will move unseen. This path and any changes hidden from direct view. This blackout isn't just a scheduling inconvenience. It means the defining moment's perihelion, the closest approach to the Sun, and any possible orbital maneuver will unfold beyond our ability to watch. The distance from Earth to the Sun is about 150 million kilometers. At conjunction, Atlas passes just beyond that at 1.36 astronomical units. No ground-based observatory can separate its faint glow from the solar furnace. Even space telescopes like Hubble and JWST are forced to wait, their safety protocols triggered by the risk of pointing near the Sun. The practical result? A data gap stretching from late October through early December. Astrometric tracking, spectral analysis, even basic brightness measurements all go dark. The only hope for a glimpse rests with a handful of solar probes and coronagraphs, tools built for studying solar storms, not distant comets. Their sensitivity and imaging cadence barely register objects as faint as Atlas. For most astronomers, the window slams shut just as the story's most critical chapter begins. Every question about natural escape or engineered capture, about comet or artifact, hangs suspended in this enforced silence. The clock is ticking, and the moment of truth will play out where no one can watch. Avi's attention snapped into focus the moment the early photometry came in. The initial size estimate for 3I/Atlas 20 kilometers across landed like a thunderclap. For context, 1I/Oumuamua measured less than a quarter of a kilometer. 2I/Borisov, the previous interstellar comet, stretched perhaps a single kilometer wide. Atlas, by comparison, was an order of magnitude larger than anything surveys expected to find first. The number itself was not a guess. It came from the object's brightness, corrected for distance and solar angle, then modeled against known cometary reflectivity. With a magnitude well above 12 and no sign of a dense, optically thick coma to artificially boost the reading, the conclusion was inescapable. The nucleus had to be massive. Loeb's skepticism grew from the math. Survey statistics predict that for every large interstellar visitor, thousands of smaller, fainter ones should have been spotted already. The Atlas survey, along with Pan-STARRS and Vera Rubin, scans the sky every clear night, tuned to catch exactly these fast-moving sun-grazing objects. Yet the first 2 interstellar discoveries were small, and now suddenly a giant appears. The odds by any population model strain belief. If the size estimate holds, either the surveys have missed a vast population of smaller bodies or something rare and unexplained is at play. This is where Loeb's argument begins. A 20 kilometers interstellar object so soon after the first 2 defies the power law expectations that underpin modern survey science. The statistical alarm bells rang not because Atlas was bright, but because its sheer scale contradicted everything astronomers thought they knew about what should be out there. For Loeb, that single number, 20 kilometers, became the first and most glaring anomaly in a growing list. A mass of at least 33 billion tons now anchors 3I/Atlas in the record books. This figure, drawn from dynamical modeling and the comet's persistent brightness, dwarfs every confirmed interstellar visitor before it. Yet the paradox begins here. Despite a vigorous outgassing rate near 100 to 150 kilograms per second dominated by carbon dioxide, there is no measurable non-gravitational acceleration. In comet science, this is the classic rocket problem. Outgassing acts like thrusters, pushing the nucleus ever so slightly off its predicted path. For typical comets, even modest activity leaves a fingerprint in the astrometric record. A slow drift, a subtle curve away from pure gravity. But the Minor Planet Center's global dataset, spanning over 4,000 positional measurements, finds no such deviation for Atlas. The upper limit on its non-gravitational acceleration is less than 15 m per day squared. So low that for its observed activity only a truly massive object could remain so unmoved. The numbers sharpen the contradiction. Take the measured gas production, multiply by the outflow velocity, and divide by the estimated mass. The expected reactive acceleration should be visible in the data unless the nucleus is not only large but remarkably dense or the outgassing is perfectly balanced in all directions. Monte Carlo simulations sweep through every plausible combination of nucleus size and density. For anything smaller than about 5 kilometers across or less dense than 1,000 kilograms per cubic meter, the math breaks down. Outgassing would have kicked Atlas off its predicted track long ago. Only a massive solid body fits both the photometric and dynamical evidence. Alternative explanations like jets firing in perfect opposition or a swarm of loosely bound fragments require fine-tuned physics and improbable geometry. The mainstream model struggles to reconcile the numbers without invoking statistical flukes or special pleading. For Loeb and his colleagues, this is not just a curiosity but an open invitation. If the mass is real and the acceleration is absent, the door to non-natural scenarios remains ajar. The first images of 3I/Atlas unsettled observatory teams. Instead of the expected tail, a concentrated forward glow dominated the sunward side, a brightness that resisted every correction for motion smear or instrumental artifact. Imaging analysts at Gemini South and the VLT pored over the data, searching for a technical explanation, but the asymmetry held. As the comet moved closer to the sun, the glow faded and an ordinary tail began to stretch away, aligning with solar wind. Some saw this as a trick of geometry, others as a sign of real change. Perhaps a crust breaking open or a sudden burst of activity from beneath the surface. Spectroscopists shifted focus to the comet's chemistry. JWST's NIR spec in a narrow window before solar conjunction captured a volatile ratio that defied expectations. Carbon dioxide outpaced water by nearly 8:1. For solar system comets, water is almost always the dominant volatile. This ratio hinted at a nucleus either preserved in deep freeze since interstellar space or covered in a layer of carbon dioxide frost. Calibration teams urged caution, flagging the result as provisional until more data could confirm or challenge the finding. Theories multiplied. Some pointed to a carbon dioxide crust shielding a water-rich interior, others to possible contamination or model error. The debate spilled into late-night Slack threads with every team defending their interpretation. Then in late September, a sudden surge of green emissions swept through the coma. Both amateur and professional astronomers reported the shift, tracing it to C2 or CN molecules fluorescing under solar ultraviolet. For most comets, green appears near perihelion, but here it arrived early and bright, outpacing predictions. The color change raised new questions about the layering of volatile ices and the comet's surface chemistry. Each anomaly, optical, chemical, chromatic, stacked uncertainty atop uncertainty. With the comet slipping behind the sun, the answers would have to wait, leaving its true nature suspended between artifact and revelation. Avi's case hinges on a window so brief it barely registers on the cosmic clock. At perihelion, October 29th, 3I/Atlas will be moving at nearly 44 kilometers per second. An interstellar bullet arcing just 1.36 astronomical units from the sun. For any object on a hyperbolic path, this is the one moment where a single push, a change in speed of just a few kilometers/s, could tip the balance from escape to capture. The physics are unforgiving. To swing from an outbound interstellar trajectory into a bound solar orbit, Atlas would need a delta V of roughly 8 kilometers per second delivered at the moment of closest approach. Anything less and the comet races on, never to return. This maneuver, if it happens, will be invisible. The sun's glare blinds every telescope on Earth. Even the best space-based coronagraphs will struggle to pick out a faint, fast-moving speck against the solar background. Detection limits for these instruments hover around magnitude 8 to 10, far too bright for a comet like Atlas during solar conjunction. The practical effect: any change in trajectory, any burst of activity or engineered thrust would slip past unnoticed until the comet reemerges weeks later. The Mars flyby, just 29 million kilometers distant on October 3rd, offered a brief hope for direct imaging. High-resolution planners debated the possibility, running calculations on angular size and apparent brightness. The numbers shut the door. At that distance, a 20 kilometers object subtends less than 0.15 arcsec, smaller than high-res's diffraction limit. Even as a point source, Atlas would be too faint for detection. No surface features, no jets, no probe drops. The most powerful camera orbiting Mars can only watch the darkness. For Loeb and his supporters, this enforced invisibility is both a frustration and an opportunity. If a maneuver is attempted, the evidence will be written into the comet's orbit, waiting to be read when Atlas steps back into view. Tom Statler, NASA's lead small-body scientist, draws a clear line in the dust. It looks like a comet. It does comet things. It very, very strongly resembles in just about every way the comets that we know. That's the baseline. The mainstream view holds that 3I/Atlas fits, if awkwardly, within the wide, unruly family of natural comets. Unusual mass, statistical fluke, odd chemistry. Comets are messy. Trajectory quirks and planetary flybys. Coincidence multiplied by the vastness of space. Astronomers like Karen Meech and Chuanji Yi echo this stance, pointing to selection bias, patchy survey history, and the unpredictable behavior of volatile rich bodies. For them, the burden of proof lies squarely on the extraordinary claim. Avi Loeb approaches the same data from the opposite direction. He doesn't use a formal scale, but his argument stacks anomalies. Mass, size, ecliptic alignment, planetary encounters, chemistry. The more these features cluster, the stronger the case for paying close attention. In Loeb's view, when enough oddities pile up, the only responsible move is to maximize observation, especially when a rare event like perihelion behind the Sun could conceal a defining maneuver. He never assigns a number, but the principle is simple. If the list of outliers grows long, treat the object as if the stakes are high. The next critical window opens in early December when Atlas reemerges from solar conjunction. Every major observatory will be primed to check for changes in orbit, rotation, and spectrum. By March 2026, as Atlas nears Jupiter, a second round of data will test whether its path remains hyperbolic or if something has changed. The decision framework isn't about scoring anomalies. It's about tracking concrete, falsifiable predictions. If the orbit stays the course, the natural model holds. If it doesn't, the debate will enter a new phase. For now, the only certainty is that the story depends on what the data reveal when the blackout ends. On October 29, 2025, 3I/Atlas will pass behind the Sun, cutting off all Earth-based observation at the precise moment Avi Loeb claims a reverse slingshot maneuver could anchor it in our solar system. The object's estimated 20 kilometers size and mass of at least 33 billion tons, combined with negligible non-gravitational acceleration and a carbon dioxide to water ratio near 8 to 1, defy expectations for a natural interstellar comet. Yet, as of today, no direct evidence confirms any artificial origin. NASA's official position remains that comets can exhibit unpredictable behaviors, and many questions such as the source of its green spectral phase and the true nature of its trajectory are unresolved. When Atlas emerges in December, its new orbital elements and chemical signatures will provide the final test. Until then, the only certainty is the need for rigorous observation and open scientific debate.